Hey guys, my name is Jason with Mount Baker Mining and Metals, and on today's video we're going to run a sample of ore through our Turnkey system behind me. So on one of the previous videos I did, I went out and collected some hand-picked samples off an old ore dump pile, brought them back, crushed them down, and sampled them, and got some pretty good results. So since then I've gone back, I've I got a bigger bulk sample from that dump pile. I brought back 250 kilograms, and we're going to run it through the jaw crusher, hammer mill, and onto the shaker table, and do an analysis of the ore. And we're going to look at the percent recovery. We're going to figure out how much free gold we have, how much is left in the tailings. But first, I wanted to show you the characteristic of the ore we're going to be running. This is a vein quartz ore. It's got some sulfides in it, primarily pyrrhotite. There's also a little bit of chalcopyrite. And now with the price of gold being up, this dump pile may be profitable to process. So here's a quick walkthrough of our 1 ton per hour turnkey system. It starts here with an 8-inch by 12-inch jaw crusher module. You fill the hopper with ore. It vibrates the material down through the jaw crusher where it gets crushed to about 3/4 inch minus. Falls down onto this conveyor belt, comes up into this fine ore bin here. And this collects the material because the jaw crusher can crush fast and it has surges. This is the ore bin that holds the material, and then we have a feeder out the bottom that you can adjust and evenly measure the feed rate. Out onto this conveyor, which goes up into our 16-inch by 12-inch hammer mill. This hammer mill has a 0.8 millimeter screen in it, and with that size screen, the crush size is about 70% passing a 30 mesh and 50% passing a 50 mesh screen. In the hammer mill, we have 20 high chrome iron hammers, which are very abrasion resistant, and they spin around at about 1200 RPM and crush the material. You add about 1 gallon or 2 of water per minute to help flush the system. It makes a really nice wet slurry that comes down this chute and runs right onto our 4x8 shaker table. The shaker table has grooves where the gold comes down and collects in the grooves. The motion of the shaker table moves the gold and the heavy minerals and elements across the shaker table to come out these top grooves. The gold and the densest material will work its way down under the water bar. The sulfides will form a band that goes down here into the number 3 port. The gold and all the high-grade material is going to be collected right here in number 1 and number 2, where we can then pan or direct smelt to recover our gold. The tailings from the shaker table come down and fall into the spiral classifier here, and the spiral classifier serves 2 purposes. One, it classifies the material. As the fine crushed tailings goes into the spiral classifier, only the fine material stays suspended in this basin and are washed out into the final tailings pond here. Anything larger than about 200 mesh sinks down in this basin and is augered out, also dewatered with this screw. Now, if there's enough value left in the oversized material, the dewatered material from the spiral classifier, these can be recrushed through a ball mill to release more gold. one of our strategies for developing a mine site or processing old dump piles is to start out with a bulk sampling type program where you can get some equipment on site and do bulk sampling in the tens or hundreds of tons through the jaw crusher, the hammer mill, and onto the shaker table. You're going to learn a lot of information about the amount of gold you have, the percent recovery, the values in your ore, the grind size, and then once you have all that information, you can make a really good educated decision about how to improve the system that you have. And so that may be replacing the hammer mill with a ball mill, that may be focusing on grinding to a finer size, maybe 80% passing 100 mesh. But the whole idea is to start with a fairly low capital expense. The equipment will give you the information that you need, well paying for itself by processing the ore you have. And all the tailings, all your material that you processed, you can save. Even if there's gold left in the larger material, you can reprocess that later, but don't spend millions of dollars setting up a mill before you have the information. Get some good testing done and then expand on that process and recover the gold that is still in your tailings if there's value to be had there. The system behind me can process somewhere in the neighborhood of 1/2 to 1 ton per hour. It's not only bulk sampling, but it's actually small scale production. It's large enough where you can process several tons per day and get a lot of information about your ore, but it's small enough that the expense and the operating capital is kept fairly low. And then if your ore or your dump piles or your mine proves out and you want to scale up, you can always increase the size of the equipment. You can replace the hammer mill with a ball mill. You can get a larger table for more throughput. So our equipment really is like building blocks where you can start with some equipment and replace the pieces as you need to scale up or change the design or grind finer, where it's not like you have to replace the whole system to grind finer or replace the whole system to get more throughput. Here's our samples from the shaker table and running our 250 kilograms. Here is the material off of the number 1 port. There's hardly anything in there. Here's the number 2 port, a little bit more, mostly black sands and sulfides. This is our number 3 middling. We'll take a sample of this. We'll do an assay here in our lab, and then we'll send an assay, a sample off for assay at an actual assay lab. And then here's the number 4, and we'll do the same thing. We'll do an assay on this, try and get a grams per ton, and then we'll send an assay of the tailings off to an assay office and get that assayed. Here's the number 1 from our shaker table, and we'll play with each one of these separately. And there's such a small amount of material here that I'm just going to take it and direct smelt it. I'm going to put it in a frying pan, put it on the furnace for a minute and dry it out. Not necessarily roast it, but I'll dry it out and then mix up a flux recipe, and we can get the smelting in our furnace and recover our gold. All right, we got our stuff drying out, and just by kind of default, a little bit it's going to roast, but we got it pretty well dry. Get rid of these little pellets here. But now that it's dry, we'll get it pulled off and we'll mix up a flux recipe here. All right, so we have our number 1 concentrates from our shaker table. We've dried them out. They weigh just right about 200 grams. So we're going to mix up a flux recipe now so we can smelt those down and get our gold out. So our first component is anhydrous borax, and we're going to use 200 grams of anhydrous borax, so the same weight as our material that we want to smelt. So there's 200 grams of anhydrous borax. And I like anhydrous borax because it doesn't have the water and it doesn't bubble and boil as much in the crucible. You don't have to drive off all that water, and you can use less material because you don't have the water weight in it. And borax for our flux is it's an acidic flux, so it makes it real glassy, and it's really, really good at absorbing or dissolving oxides, metal oxides, so your iron oxide, copper oxide, lead oxide. And also it absorbs all the silicates. So any silica that's in there, the rock particles, all the junk that we don't want in there. So that's what the borax is for. The next one we're gonna do is lye. And somebody asked me the other day, the typical thing is soda ash. People usually use soda ash. And why am I using lye was the question. And I use lye because soda ash and lye decompose to the same chemical when they're heated. And they decompose to sodium oxide, which is Na2O. And when you decompose soda ash, or when you heat it up, it has to drive off a whole bunch of CO2 before it gets down to the Na2O. Whereas with the lye, you just have to drive off one molecule of water per 2 atoms of lye, which is sodium hydroxide, which is NaOH. So you drive off one water molecule for every 2 molecules of lye. And so again, you're driving off a lot less material. It bubbles much less. It has a much lower melting point as well. And so that's why I like to use lye. And also you don't have to use as much. So with soda ash, I'd probably have to use 250, 300 grams of the stuff to counteract all that carbon dioxide going off. But for our lye, I'm gonna use 200 grams as well, so equal parts borax and lye by weight. And we use the lye because it's a really strong base. It's really basic. And when if you have sulfides in particular, we're gonna put an iron rod in there, which is gonna reduce some of the less reactive metals such as copper and lead to metallic form. You're gonna form FeS, which is an iron sulfide. And when you make your slag pretty basic by adding the lye, it makes it so the slag can absorb that FeS matte, that sulfide that we're gonna make. And whenever you smelt, you wanna have a slag layer and the collector metal layer. If you have any matte layer, which is undecomposed sulfides, you're gonna have precious metal loss. So that's why we have our borax. And then the last one is gonna be silica sand. And this is also a very acidic base, or a very acidic flux. And it does a good job of absorbing the metal oxides as well. But for the silica, we're only gonna add 100 grams of silica because if you add too much silica, it makes the flux really, really thick, and you want your flux to be fairly fluid so the metals can fall to the bottom and collect in the collector metal. And you don't want it so thick that it's hard to pour, or it gums up, or you have little metal beads stuck in your slag. You want it to all collect down in the bottom. So there is our charge. I'm gonna mix that up, and then we're gonna put it in a number 5 crucible here. We're gonna put it in our furnace. I'm gonna add an iron rod in there to reduce those other base metal sulfides, and add a little bit of lead as a collector metal. And once we get our lead collector metal, we can take it over to our Cupel furnace, Cupel the lead away, oxidize the lead away, and we'll be left with our precious metal bead. So I just take like a 2-gallon bucket, put all my stuff in there, and you can just mix it up. You probably want to use a lid. The lye that we use is really, really caustic, and so you don't want to get it in your eyes or on your skin because it'll start eating you alive, literally. And then once it's all mixed, I'm just gonna get it in our crucible here. And so here's our crucible, there's our charge. That's pretty full. That's about as full as you want to get a crucible. Just because as this heats and expands, it's gonna increase in volume just because it's getting warmed up and heated. And then when it's all liquid, it'll actually probably go down to about half full. But that's another reason why I like to use that anhydrous borax and the lye, is because if you have to drive off a bunch of gas out of this, it tends to froth up and boil, and it can boil right over your crucible all into your furnace. So we'll get that put in the furnace, we'll get it heat up. On a cold heat, it usually takes about 30 minutes, maybe 40 minutes for something this size to heat up and get molten. And then once it's molten and the reactions have all taken place, we'll pour it into our cone mold and get the collector metal down at the bottom. Okay, it might be kind of hard to see, but our crucible's down in there. We've got an iron, a piece of steel rebar in there. I've added 50 grams of lead as a collector metal. And on a cold start like this, we're going to heat it up kind of slow. And once it gets kind of warmed up in there, I'll turn up the gas and the blower and we'll really get fire in it. So I can tell by the way it's cooling that it's pretty basic. It stays molten a long time. Those white fumes coming off tell me it's basic, and it's got that white halo around the cone mold. And as it cools down, you can see the convection cells. And what's going to happen here really quite soon is at the corners and intersections of all those convection cells, it's going to start to form a little bit of a skin on top. And that skin will grow right to the middle of those convection cells and cover the whole surface. But like I say, when it's very basic, when you add a lot of lye, it stays molten for a long, long time because lye in particular has a very low melting point. But you can see that little bergs of slag starting to form that skin. It's cooled down quite a bit. It's not even orange anymore, hardly. And it's going to seal itself off here in just a second. And hopefully all of our collector metals down at the bottom, well, hopefully it is, and our precious metals are in that collector metal button. And when the slag cools down, we'll turn this over and we'll pull that collector metal button off and cupel it and recover our precious metals. Anyway, it might be hard to tell in the video, but it's just a lead button. There's no mat on top. It's just goes glassy slag all the way down to the lead. So that was a good decomposition of those sulfides. And the iron bar really helped to take all those other base metals and sulfides, turn them into FES, and then dissolve them into that slag we made. So I'm going to take this, pound it into kind of a block so it knocks off a bunch of that slag, and then I'm going to put it in a cupel and put it in our furnace. So there's our little lead button. I've knocked pretty much all the slag off it, but it's really hard, and you can see right there, it's cracking. Which tells me there's a lot of other metals in there other than lead. If it was mostly lead and gold and silver, it'd be real soft and I could hit it. But that iron rod probably reduced quite a bit of copper or maybe some other metals in there that are making it hard and brittle. So we'll see how this cupelling process goes. This is our lead block from number 1. And I don't know if you can see there, but the lead oxide's molten and it's kind of running over into the cupel. So let that go and hopefully get a little gold bead when we're done. All right, here's our gold from the number 1. Nice little button there. And it's still smoking hot, but let me see if I can do this and video at the same time. It shouldn't be attached to the Cupel. It should just pop out of there. Yeah. So there's our gold bead. And there you go. Our beads cooled down. And just from the number 1, we got 3.74 grams. All right, here's dried out material from the number 2 off the shaker table. And we ended up with 1,300 grams after it was dried. So I took that material, I split it in half. So I have 650 grams of the number 2 here. I mixed it with 650 grams of borax, 650 grams of lye, and 325 grams of silica sand. So it's 1 part ore, 1 part borax, 1 part lye, and half a part silica. And I'm going to use this clay graphite crucible. I think this is a number 10 or a number 8. And I want to see if the clay graphite can hold up a little bit better than those fire clay ones for getting eaten up and getting dissolved in this basic slag we're making. So we'll get this fired, pour it in the cone mold. I'm going to add 50 grams of lead to this as a collector, and then I'm going to have to do it twice because I have so much material I can't fit it all in one crucible. But we'll get the number 2 processed, and then we'll Cupel down the 2 lead beads, get them together, and see how much gold is in the number 2. Well, it's my first smelting disaster. I went to pick that thing up and I grabbed it with some tongs kind of right there, and the crucible broke and it flipped on its side and it all oozed out all over the place. So darn. Well, we'll have to get this cleaned up and figure out what we can salvage, and there should be 50 grams of lead and gold in there somewhere. So hopefully we can find it in all this mess and recover it. Okay, well, here's the wreckage. So I pulled all the fire brick hearth off and kind of got all the slag and all the junk in one pile. And funny enough, well, that crucible was tipped over on its side. There was still, I don't know, a little bit, a quarter cup worth of stuff in it. And so I poured it into the cone mold just kind of more by reflex. And that's where most of the lead was. There's a little lead bead. There was a few little splashes and stuff that I picked up. But I'm going to get this weighed and figure out, I put in about 46 grams. So let me figure out how much lead I have left. And maybe we can just go ahead with the results without having to deal with this mess. But just to do my due diligence, either for the rest of this test or sometime in the future, I'm going to take all this stuff and crush it up and probably run across the shaker table. And if there's any little beads of lead or other metals in there, I'm going to recover them and smelt them down just so it's not lost. But my hope is that most of my metal is here that I recovered just kind of by accident. Well, we have almost 35 grams worth of lead, so we actually recovered most of our collector metal. So I'm just going to keep going. I lost about, I don't know, 20 to 25% here. So we can, in theory, add 25% more metal than we get out of this. And I still have 650 grams of the concentrate that I still got to smelt. So I think if we put a little factor on it at the end when it's all said and done, we can come out with a pretty good amount of metal. All right, well, I need a new furnace anyway. So I got my 2 cinder blocks under there. I'm working on a fire brick hearth, and now I'll put the KO wool on top. There's our wrapped KO wool. Got our number 12 crucible in there for size. So now we got to cut our hole and put a top on it. And there we go. I cut a little mouse hole for our torch, and I recycled some of that old KO wool back on for a top. I got a little different design. I'm going to split it in half and see if that works a little bit better, but we're ready to get going again. A little pain in the butt, but we're back and running. And there's our stuff cooling down. It's that cool pattern on top as it cools. Those convection cells rising up. And there's our little lead bead off the top of the pyramid. And now what I did is I actually took all the collector metal from the first first half of the smelt, and I put it back in. So I doubled up this collector metal with gold. So all the gold from the number 2 port from the shaker table is here in this bead. And there's our bead. I kind of hammered it down, hammered all the slag off of it. And now we'll put it in a Cupel and put it in the furnace. And here's our number 2 right out of the Cupel furnace. So we got our little bead there. We'll get her cooled down and weighed and see how much we got. And that little guy weighs 0.30 grams. Here's our number 3 middlings off the shaker table. And they weigh 9 kilograms. I took off about half a kilogram for the water weight. And I got them all mixed up. I'm going to take a sample of this, dry it out, and then we'll smelt it down. Here's some of the number 3 middlings. And I've gotten them dried out about 100 grams, smelt them down just like we did with the number 1 and number 2. See how much gold we can recover from the number 3. Here are the last 2 Cupels. This is the number 3 middlings and the number 4 tailings. So we'll get those Cupelled away and see what the beads look like. All right, guys, so here are the 4 Cupels. This is the number 1 with the big gold bead. This is the number 2 with the silver colored bead. The number 3 middlings here, 100 grams, number 3. And there's a bead there. It's pretty small. And then this is the tailings that also has a little teeny tiny bead in there. And again, these 2 both had 100 grams of material. We smelted all the number 1 and all the number 2. And I went and got some XRF readings from the number 1 and the number 2. So I'll show you those now. First, the number 1. And now the number 2. This one weighs 3.74 grams. This one weighs 0.30 grams. And we'll get these out in a minute here and weigh them on our superfine scale and see if we can get a weight on those. All right, here's our new tool. We've got a scale that reads down to 0.0001 grams. So that's a 1/10 of a milligram. And a big shout out to Chris Ralph on this one. I thought these were, thousands of dollars, and I found them on Amazon for between $300 and $500. So if you need one, they're really not that bad, and they get you down to 4 zeros of a gram. So that's pretty cool. And so we've got our number 3 and our number 4 here. But before we do that, we have to figure out how much silver is in our lead. And so I did a Cupel with 30 grams of lead, and there's the little bit of silver we got out of those. So this really doesn't matter when you're doing big smelts where you're getting, multiple grams or even tenths of grams of stuff. But when you're doing these tailings samples or these other little tiny beads, you really got to figure out how much silver's in your collector metal so you can subtract that out so you don't, get twice as much precious metal as you think you do. So let's get our lead collector bead weighed, and then we'll know how much to subtract off our number 3 and number 4 bead so we can get an accurate result. Okay, so our residual silver in our collector metal weighs 0.0008 grams. And our button from 100 grams of our number 3 concentrates, our middlings, weigh 0.0049 grams. And so we got to subtract our 0.0008 grams from that. So we really have 0.0041 grams. So the bead from our tailings is 0.0027, but we'll subtract the collector metal off there. So we really have 0.0019 or 18.
All right, guys, I'm just going to go over this real quick. Here's how much our collector metal silver weighed. These are the adjusted weights of the beads in grams, and this is the adjusted weights of the beads for the gold. And I used the same XRF reading for number 2, and I just duplicated it for number 3 and 4. And here's our quick calculation. We're trying to figure out how much gold's in each fraction. So the number 1 and number 2, we recovered all the gold at 3.12 grams. The number 3, we had 0.0017 grams of gold. We had 9 kilograms of the material, so there's 0.153 grams of gold in the number 3 fraction. And the number 4, the same calculation, we have 1.80 grams of gold left in our tailings. And when you subtract the amount from number 1, number 2, and number 3, we had 240 kilograms of tailings. Now let's figure out our percent recovery. And here's our total amount of gold in the 250 kilograms. This is a little over 5 grams. So multiplying that out times 4, you get just over 20 grams of gold per ton. So that's pretty good, about 2/3 of an ounce or so. And then our percent recovery, we add 1, 2, and 3 together. We get our 3.273 grams, divide by the total amount of gold, and we end up with 65% recovery. So not terrible for a gravity recovery circuit. I was hoping to get a little bit more. But now let's go and take a look at our tailings, screen our tailings down, and see if we can figure out where the gold is hiding in our tailings fraction.
So here's the number 4 shaker table tailings, and we've got them dried out in the sun. Now we're going to take them and we're going to screen them through a 50 mesh screen and a 100 mesh screen. So we'll get 3 fractions. We'll get 50 mesh plus, we'll get 50 to 100, and we'll get 100 minus. And then we're going to take each one of those fractions and weigh them to figure out the percent weight of each sample, and then we're going to assay them and see how much gold is in each fraction, and that way we can determine if all of our gold is in the 50 mesh plus that we just need to grind finer, or if a lot of our gold is in the finer stuff, but it'll give us a lot more information about where to target for better recovery. This will be another good test actually to figure out the grind size from the hammer mill. And like you may have saw in the video, when I was taking samples, I took them right out of the number 4 port on the shaker table. I didn't take them out of the spiral. And so this has all the fractions that the hammer mill grinds to. It hasn't been classified or augered out or dewatered yet. Here's our 50 mesh plus, and this was 54% of the total weight. Then we had our 50 to 100, which was 18% of the total weight. And then we have our 100 mesh minus, which is 27% of the total weight. And then here's a close-up of that 50 mesh plus. And so you can see it's fairly coarse. You can see the individual grain sizes. It's kind of would be a beach sand. This is 50 to 100 mesh. And there again, you can still kind of see the individual grains. It would be a fine sand. And then this is the 100 mesh and smaller. And here you kind of lose the ability to see the individual grains. It's really powdery and cakey. So that gives you kind of the idea of the size of the material we're talking about when we talk about mesh size and different sizes like that. So we'll take a section of each one of these and get them assayed, and we'll see how much gold is in each one of these fractions. And there's your lead button right there.
And it's a little bit hard to tell, but there's no mat on top. It's glassy slag all the way down through right to the edge of the button. And so we'll get this kind of pounded into a little bit of a cube, knock all that slag off, and we'll put it in the furnace and get it cupelling.
So this is our little electric furnace that we're using to cupel our lead. And we have our 3 samples in there, our 50 plus, our 50 to 100, and our 100 minus. And so what actually goes on here with the cupelling process is the cupels are made of bone ash, or I think it's magnesium oxide, which is porous to oxides, but not to metal. And so you have your little dish, you put your lead metal in there, the collector metal from our smelts. As you bring it up to temperature, the lead melts at about 650 degrees or something. So it turns liquid, and it forms a layer of lead oxide on top. And it looks black, it looks scummy black. And then as you raise the temperature more, the lead oxide becomes liquid. It actually melts at 1640 degrees Fahrenheit. And once it melts, it looks like little raindrops on top of the lead metal. And once it becomes molten and melts, it rolls off the lead bead, and when it touches the cupel, it sucks into the cupel like a sponge. But that lead metal button is impervious, or it's impervious to the cupel, and so it constantly forms an oxide layer on top of this molten lead button. The oxides are shed, absorbed by the cupel, and that process repeats until your lead button just shrinks all the way down to a little precious metal bead in the bottom of your cupel. And if you have, the button is a huge percent of it by weight is lead. But if you have any iron in there, if you have a little bit of copper in there, if you have arsenic, bismuth, those will all oxidize as well, and the lead oxide sheds those off into the cupel as well. If you have too much copper or nickel in particular, the oxides, as they rise to the top, the copper and the nickel, they have a very high melting point, and so if you have too much, the copper or nickel oxide will actually cause your button to freeze. And it's not a big deal. You just take your frozen button, you put it in another cupel, add more lead, and keep shedding until you end up with your precious metal button. But if you have too much copper or nickel, you may have to cupel it many, many times. Also, with copper in particular, if you have a lot of copper, those copper oxides bring precious metals with them as they go into the cupel. And not a bunch. I mean, we're talking maybe 5% of your total button. But it's certainly enough when you're talking about assaying or getting really accurate. You want to be aware of copper and nickel in particular.
So here's our beads from our tailings, 50 plus, 50 to 100, and 100 minus. But this cupel I just did, this is our blank lead sample. And you can see there is a little bead of precious metals in there. Here's our 50 plus, 50 to 100, and our 100 to 200. So here's our screen tailings fractions. There's the weight of the bead, subtract the collector metal, and here's the weight of our beads in gold and silver. And then down here I've taken out roughly half of the gold and silver based on our XRF reading. And so you can see where most of the gold is in the tailings. Now I've added the weight percentages of each, so let's do some math and figure out where our gold is in our tailings. Okay, so now here's our 3 fractions, and an example calculation is our 50 plus material had that much gold in the assay bead. You multiply it by 2400 to get from 100 grams of our assay to 240 kilograms of our sample size. And then you multiply the 0.54, which is the percent weight of that fraction. And that's how much gold you get in that fraction of tailings. And so continuing our math down, here's the amount of gold total in our tailing sample. And you'll notice there's a little bit of a discrepancy here. Our original tailings, we figured there was 1.8 grams, and this is about half of that. So, there's a little bit of discrepancy in the tailings. And surprisingly enough, if you use this amount of gold for the tailings, we actually recovered somewhere closer to 79% recovery as opposed to our 65%. So we're kind of in that range of 65 to 75% recovery probably. And then here's the percentages of where the gold is. So 50 plus has 59%, 50 to 100 has 34%, and 100 minus has 7% of the gold. And so now, kind of continuing on our train of thought here, if you ground all the material to 100 mesh minus and you end up with 0.240 grams of gold in 240 kilograms, you would end up getting about 94% recovery if you ground it all to 100 mesh minus.
So we covered a lot of ground, and we looked at all the details on our recovery and our grind size and all that stuff. Now I wanted to pull back and look at some of the bigger picture and do kind of a rough back-of-the-napkin analysis of what we could expect if we implemented the system up near the dump pile on this claim. So we're recovering about 75%. Plus or minus, and with 20 grams a ton in the ore, that means we're recovering about 15 grams a ton. For an operation standpoint, you figure you can run 6 hours a day. That's 6 tons. That's about 90 grams of gold. The operator is going to cost about $50 a ton. The system costs about $50 a ton to operate. You're going to need an excavator or loader. Let's put $50 a ton on that, and then an extra $50 a ton just for being conservative. So you're about $200 a ton to operate. And let's say we operate for 8 hours a day. So those are our costs for 8 hours a day. That ends up being right around $1,500. At 90 grams of gold recovered a day, that's about $4,500. So you're looking at about a $300 or a $3,000 spread there. And just for fun, let's double our cost. We'll say, okay, it's not going to cost us $1,500. It's going to cost us $3,000 a day to operate. We're still coming out making about $1,500 a day. So I wanted to emphasize that around the Western United States and the rest of the world, there could be lots of dump piles, tailings piles that have now become profitable due to the increase in price of gold. And so with the system behind me, you can see how easy it is to implement, put it on site, and start producing gold, getting a lot of information that you need, getting a gold product, and it's easy to take this system and expand it into a larger system once you have the information that you need to do so. Also, one of the other things I wanted to point out here is you don't need to start with the full turnkey system. You can get a lot of information with just the hammer mill and shaker table behind me, or even a hammer mill that's powered by a gasoline motor and run down into a sluice, which we're working on, and I know a lot of you guys are really excited to see that. So we'll have a video of that coming soon. But the turnkey system is really designed for people who have some knowledge of their claim, have done some analysis, and are ready to go for the next step into small scale production or bulk sampling. But again, for a lot of you small scale guys, or you guys that maybe don't have the budget or the tonnage to do 1 ton an hour, start feeding by hand and start small. And if you prove up the property, get some capital back from that initial investment, you already have the core components of the turnkey system. Then you can just expand with a jaw crusher, some conveyors, a spiral classifier, and build as you go, and kind of bootstrap your way along in your production and in your gold mining efforts. One of the really important parts to understand as an operator or a bulk sampler of a gold claim is your goal is not to initially recover as much gold as you can. Your goal is to get the information you need to go for the next step for investing in machinery. And so that's why we did our grind size analysis. With the hammer mill and the system as it is, we're recovering about 75% of the gold. But we found out that if you can grind to 100 mesh minus, you can recover somewhere in the 90% plus gold recovery. And so this material here out of the spiral classifier, this is still a resource. This has somewhere in the 3 to 4 grams per ton of gold as it sits. And so you don't want to throw that away. We haven't lost any gold. The value is still there. And so as you get your capital up, or you're starting to produce a profit and get some money, you can take this pile and recover the gold out of it. Because there's about $100 to $150 worth of recoverable gold a ton here, and you don't want to throw that away. And that's where a ball mill comes in. You can purchase a ball mill, you can leave the entire system the way it is, and actually if it were me and I was going to implement a ball mill into this system, I'd take our spiral classifier, I'd put a ball mill right here, I'd divert the spiral classifier right into the ball mill, I'd increase the table to a 2 ton per hour table, and I'd run the ball mill directly onto the table with the head ore. So anything that goes out of the spiral classifier into the tailings is true tailings. Anything that gets augered up goes through the ball mill and is reground and put right back directly onto the same production table that the head ore is running. And so all the values are going to end up going over in the number 1 or number 2. So that's one way that you can increase your production or increase your recovery by adding a regrinding circuit to your production. And so the question we have to ask is, right now we're recovering 75%. We can recover 90% if we regrind this, but is it profitable to do so to get that extra 15%? And by introducing a ball mill, which has a very low cost of maintenance and wear, and if you have a large enough resource through the tailings, it probably makes sense to go after that $100 to $150 worth of recoverable gold a ton if you can keep the system moving and have the resource to justify it. The last thing I want to mention is that if you're in the gold mining industry, you know that there's lots and lots of properties out there, and there's lots and lots of properties for sale. But whether you're working your claim yourself, looking to sell the claim in the future, or looking for further investment, if you have a gold property that's actually producing gold, whether that's run-of-mine stuff that you're mining or reworking the dump and tailings piles, having a product that you can make that's gold and then sell, producing off your claim, makes your property unique and way, way more valuable. And so having the turnkey system producing a product makes you way more attractive to a potential buyer or potential investors to really increase your production and get your property up and producing on a larger scale. So I hope you guys enjoyed the video. If you have any questions or comments about our equipment or anything you saw on the video today, you can find our contact information in the description below. So thanks again for watching, and we'll see you on the next one.